This is a presentation about DevOps, and running code in the cloud. It's a story about the changing nature of organizations that produce software and the technology that's driving that change. Recall what happens when you visit a website. Here I'm visiting reddit.com, which I probably read 50 times a day. Your browser makes an HTTP request to reddit.com, and a server-side web application sends back responses. So it might send back HTML, CSS, and JavaScript, or images and things of this nature, cat GIFs, whatever it is. And many clients connect to this single server, and that's called the client-server architecture. Now, inside the server, as we discussed in class, there's a stack that looks akin to what you see on the right-hand side. There are applications that request resources from the operating system. The operating system runs on top of the firmware, which helps the operating system communicate with the hardware, communicate and control the hardware. So, for example, how does the operating system know how to control the CPU? That is through the firmware. Now, there are many more applications running on the server than I described in previous classes. In previous classes, we focused on only those applications that we were writing, and those are represented here in this box on the right-hand side by App 1, App 2, App 3. In truth, when an HTTP request comes in, there might be a variety of things that handle that request. So, for example, it might first be processed by a cache like Varnish, and that would help us respond very quickly to things that we've seen previously. So, for example, if someone's requesting the most popular image on Reddit, that is probably served by a cache. And then the request might be passed off to an HTTP server that's acting as a reverse proxy like Nginx. And Nginx might pass through some of those requests to various applications. Indeed, our course website looks something akin to that. There's an application that runs the main course website, and there's a separate application that has the Q&A system, and the reverse proxy, which in our case actually is Nginx, filters which requests go to which applications. What I'm showing on below App 1 here is that application requires access to a variety of things. Maybe it needs access to the file system to read files that are on the computer. Maybe it needs access to a database to store data about students, for example, or bank accounts, or whatever it is. And in our case, that's MongoDB. It could be Postgres or MySQL or anything like that. And the application could require access to a cache like Redis, or a queue like RabbitMQ, and various external APIs like YouTube, Facebook, LinkedIn, GitHub, Instagram, whatever it is. So the question is, that's a lot of stuff, and we haven't talked about that before. So who's responsible for those things? Because we've been talking about developers, and really all we talked about was the application, and we assumed that these things were available. We assumed that you could have access to a database, or access to the file system, or even a computer to run your application on. And that's the role of an organization called Ops, which stands for Technical Operations. And Ops is traditionally staffed by people who are systems engineers, systems administrators, operations staff, release engineers, database administrators, network engineers, security professionals. And Ops is one of three organizations that you would see in a traditional company structure for a company that's producing software. So there would be Dev, and Dev are the people who write the apps. And there would be Ops, and those are the people who make sure that the resources are there to run the apps and keep them running. And there's an organization called Q&A, and we won't talk much about Q&A, but their role is to make sure that everything works as expected. And you notice here I'm not talking about IT or the people that run your printers and this kind of stuff. We're talking about people who provision resources for customer-facing products. So, the business articulates needs. Dev writes new code and gives it to Q&A, which makes sure it works, and who gives it to Ops to make sure it runs, and gives it to the customer, and the customer finally gets their value. And this is traditionally how things worked. And the problem is that it's a very long release cycle, which is to say that Dev spends a long time writing code, and then they might spend weeks on it, or whatever it is, a big batch, and they hand it to QA, and QA takes a look at it, and maybe it's got problems, and it goes back and forth, and there's a bunch of bugs and whatever. And finally, they give it to Ops, and then Ops' responsibility is to make it run in their server environment and to keep it running always for the customers who then derive value from it. And it takes a long time, and there are conflicting incentives and pain points among these various organizations due to the way that they're structured. So DevOps is a new movement which started around in 2009 that is changing a lot of software companies, and it is something of a union between these various functions, which is to say that it's part Dev, part Ops, and part QA. It's DevOps. Now, traditionally, dev has had the responsibility of building new features, and ops has the responsibility of keeping stuff running. So in some sense, dev is potential income, ops is confirmed income, and dev are the cool kids. They're close to the business, and ops is far from the business. Dev is close to the CEO and whatnot because they're developing new features, right? They're the new sexy stuff. And ops, those are the stability people. Those are the people who don't want to see a hiccup on the weekend and want to keep things how they are. They don't like new features, right? This is the traditional structure of these two organizations. And if you're confused about that, this little quote from DevOps Borat will help you out. He says, confused of dev or ops? Simple rule, if you are praised for website success, you are dev. If you are blamed for when website down, you are ops. And that's very much true. So there's a real tension in the sense that dev would develop a new feature and give it to ops, and dev would like to see that feature in production. For ops, it's kind of a pain in the butt because it's something new that they have to support. And it leads to all sorts of problems. So for example, this little girl here says, worked fine in dev, ops problem now, right? I got it working in my environment. This new awesome feature works on my laptop. I don't understand why you can't get to work on your servers. And this creates a huge tension. And that tension between ops and dev is bad for customers, and it ultimately hurts the business. Now, in 2009, some developers from Flickr presented at the O'Reilly Velocity Conference and created somewhat of a stir in their presentation when they revealed that Flickr was pushing 10 times per day to production through the cooperation between their dev and their ops operation, which is to say that they weren't waiting weeks to push out new features, or they didn't have some release 1.0 and release 2.0 is scheduled for 6 months from now after the following people check off on it. They had an organization that would push code every day, 10 times a day into production to their website that all their customers saw. And what they said in this presentation that ops' job is not to keep the site stable and fast. It is to enable the business. And the same is true for dev. Everyone has the same job. The job is to enable the business. And so DevOps is basically where dev meets ops. And there's a little bit of QA in there too. So to tell you more about DevOps though, I think you need to understand a little bit about the cloud and cloud computing, because it's one of the enabling technologies that allows these cultural shifts within organizations that are now implementing a DevOps structure instead of a traditional IT structure. Recall back to the first .com era. Back then, if you were starting a company, you probably needed millions of dollars of servers that you actually bought. So these are physical machines, and you would stick them somewhere. You would stick them in a rack, and you'd go and service them, and you would manually configure them. You'd bring a CD, and you'd stick it in the CD tray, and you'd install Linux or Windows or FreeBSD or whatever it was, and then you'd install Apache or Nginx or your application. And you had beepers because stuff broke, and you had to go fix it. You actually had to fix real hardware because you had hard drives that broke. And what happened is that we had very slow releases, and this was kind of the norm. So everything is very complicated. Basically, ops' job is very difficult because they're dealing with real physical hardware, and things break easily. You have to go manage it. Well, over time, of course, we built more and more data centers, and things got more and more sophisticated, and these are all connected by faster and faster connections, and they're huge now. So the average data center now has something like consumes the power of maybe 25,000 houses. So it's incredible the size of these things, and now the sophistication as well. But there are some problems for different organizations. If you think of an organization like Amazon, maybe they have very high seasonal demand. So around the Christmas season, everyone's ordering books or teeth whiteners or whatever it is for their spouses, loved ones, children. And the rest of the year, Amazon might do much less traffic. Well, it needs the server capacity to service the high point, and then for the rest of the year, it has more servers than it needs. And of course, if you're an MBA student, you will recognize that as a classic capacity utilization problem. And on the flip side, if you're a cool startup number 5, you don't have much money. You need servers, but you don't want to make a huge fixed investment. So the solution to this is virtualization, and it's one of the enabling technologies for cloud computing. Recall, as we said, that a server operates on something like the following stack. There's apps, which talk to the operating system, which talks to the firmware, which talks to the hardware. Now, if we look at that stack And instead, we inject in a virtualization layer, which is an operating system plus some ability for the operating system to host other operating systems on top of it. We can run many machines. So here, for example, there's hardware and there's firmware that sits on top of it, and then there's operating system and virtualization layer. And running on top of that are things that look like individual computers. So they have their own operating system, they have their own apps, and they believe they are talking to their own hardware, but they're not really. There's a virtualization layer that sits between them and the hardware, and what it allows is many different computers to run on a single computer. So virtual computers, virtual machines running on a single computer. So we replace those here with little cloud servers. And what you can do in that context is scale horizontally, which is to say that I have a fixed amount of hardware and fixed amount of investment that I've made, and I can spin up virtual servers in response to demand. So I can saturate my investment, I can use it up, I can sell virtual servers to other people, or I can use them myself and give them to different people in my organization who need compute capacity. And in that fashion, I'm not just underutilizing a single computer, but instead making the most of my capital investment. And so what has happened then is that we have virtualization that allows us to spin up computers, and not just computers, but all sorts of resources like databases and whatnot. Anything that can be virtualized has been virtualized, and there's an organization of people, which are shown at the bottom right. Those are the ops people, and they have helped to make those things accessible to dev, which is the top right, so that dev can control these things and monitor these things, which is to say that dev can control how many servers they have, they can control how the servers are configured, what's installed on them, and they can monitor those things. Dev can control how much database or CPU or whatever the resource they want is, and receive accurate monitoring of those. And so the relationship here between dev and ops is changing in that ops is not setting up these computers, physical computers for dev, but instead providing dev the tools to manage their own servers, to create their own servers, to monitor their own servers. This virtualization solves two problems. One is capacity utilization, and the other is on-demand resources. And it's the basis for cloud computing. So now Amazon, which has excess cloud compute capacity, can sell its unused computational time and hard drive resources and network bandwidth and all sorts of stuff to cool startups that don't want to make that kind of investment. Okay, so that is the technology that underlies cloud computing, and it's really enabling for DevOps. DevOps is a set of practices that are enabled by virtualization and cloud computing that breaks down the barriers between the typical organizations in a software company. So these organizations, Dev, Ops, and QA, well, they're filled with people, okay? And now those people in a DevOps world, they're not siloed into Dev, Ops, and QA with the tensions between them, but instead they have shared responsibility for the business. So in this context here, Ops, as we said in some of the previous slides, is creating an environment in which Dev can self-serve many of the things that Ops would normally have to do for them by hand. And that's all enabled by cloud computing. So for example, Dev can start up a testing machine, and that's going to be responsible for testing all the code that they have. They can start a QA machine, and that QA machine allows people to log in and look at the code that's coming out and see if there's any problems with it. And they can start different kinds of production machines. So those production machines may multiply when there's huge demand at Christmas or the Super Bowl or whatever it is. So DevOps is the practice of ops and dev and QA participating together in the entire life cycle, from design through the development process to production support. Everybody's working to the same goal, and the barriers between them are broken down. And it's powered by a certain set of philosophies and a certain set of practices. And those philosophies are a little bit touchy-feely. They're iterative, incremental, which means that we're doing small things all the time. It's continuous. Well, iterative and incremental means we do small things and we learn from them. Continuous means we do them all the time. And things are automated. We're automating all the things now. So recall in the first .com, you had to go install stuff on computers manually with a CD. No longer is that the case. Generally, you can spin up cloud machines and install stuff on them remotely. In fact, DevOps relies heavily on automating anything that can be automated, anything that is error-prone or anything that people don't want to do. We automate all those things through software. And it's self-service, which is to say that dev can serve themselves now. They don't rely on ops, and so it eliminates a great deal of tension, and it's collaborative. So everyone is focused on the business and understands that they all have the same goal. Now it's powered by a certain set of practices, and we'll explain some of these practices so that you can better understand exactly what DevOps means in real life. One is configuration as code, and that means that we have machines on which software is installed, and we have applications that have different configurations. So for example, we might have an application that's running in QA and it needs to be configured to talk to a different database in QA than it talks to in production. And that's all stored in code, so no one is manually editing it by hand. Instead, it's stored, those kinds of configuration variables are stored in code, and that code, as you might imagine, is kept under version control. Another practice is automated provisioning, so the ability for dev to create and destroy resources as they need them. Automated testing, and that means that test runs automatically. And then a variety of these that we're going to describe in the following slides, including continuous integration, continuous deployment, continuous monitoring, and automated release management. So here's a few of these. Automated testing supports a few of the other practices. So basically, automated testing means when you make commits, tests run. So here we have some Git commits. We have two people working on them, Jane and Dick. And let's look at what Dick's doing here. Let's say Dick creates another commit here. And when he does that, what's going to happen is that in an automated fashion, there's going to be a test suite that runs. And that test suite shows that Dick's code passes test 1, test 2, fails test 3, and maybe it passes the other test. And the point is that Dick didn't have to run those tests automatically. Dick didn't do a bunch of work and then discover an error in his code and have to go back and erase days worth of productivity. Instead, in a way that was totally automated and transparent to him, his tests run when he makes commits. So he's alerted instantly if he's done something that borks up everybody else's stuff. Continuous integration is taking that one step further. So continuous integration means that developers commit to the mainline daily and integration tests run in an automated fashion. So Jane is working on stuff and Dick is working on stuff. And then a couple times a day, Jane merges her code into the main line of development, which is indicated on the center. And then maybe that's the stable code. Maybe it's just the code that's the main line and everybody's working on it. But the point is that people merge their things in and then a set of tests run to see if everything's still okay. And this is really important. So for imagine that, for example, Jane is working on integrating Amazon payment system into your website, and Dick is working on PayPal, and Dick finds the need to alter some of the core payment processing code in a way that messes with Jane's project. Well, it's important that Jane not work for 5 days without discovering that, and then if someone loses 5 days of work. Instead, what happens is that they immediately notice it because they're all pushing into the main line of development, and integration problems are detected early, not wasting people's time. Automated deployment means that if tests pass, then code moves up a level automatically. So there's developers on the left-hand side, and we have different environments. One is dev, and that's where maybe the developers are writing their code. Another is testing, where tests are run in an automated fashion. So when a developer pushes up, let's say, to GitHub or to whatever the Git repo is stored, maybe tests run automatically in various testing machines. Then there's staging, which is a copy of production that is almost like production, and it's a place where developers can look at it to make sure everything is working just like it should before things move ultimately into production, and production is where customers see it. So what automated deployment means is that as a developer writes code and pushes it, let's say, to a dev machine, automated tests are run, and if those tests pass and everything looks great, then it moves up a stage. So code that you push to dev goes to testing, goes to staging, goes to production. And obviously, in that case, it's important that your tests be pretty darn good because you don't want to push borked code to customers. The point that this, the objective that this achieves for us is that it allows us to move code very quickly into production. And so, for example, at Flickr, when they were deploying 10 times per day, this is the kind of activity, automated deployment, that would support that. Another practice is continuous deployment. Continuous deployment means that you ship code to production many times per day. And in this case, what that enables is that you learn from your customers. So here we have the business or developers, whoever it is. It's ops, it's QA, it's dev, and they're pushing code, and it goes through the continuous build process and ultimately makes its way into production and is therefore delivering value to customers, right? So code equals value. We're making new features, new things that customers want, or fixing bugs. We're delivering value once we're delivering it in small increments, and those small increments allow us to learn rapidly from customers. Another best practice of DevOps is finally continuous monitoring, and that's really important when you ship to production a lot. You have to watch for problems. So one problem may be, for example, my icons in this presentation are borked. That's the kind of thing I would like to detect in an automated fashion and be alerted about. So in continuous monitoring, we have all sorts of monitoring in production. We might monitor, for example, the number of errors that users see, or exceptions that are handled by code, or file uploads that didn't work, or even comments from users for problems such that we can find cases in which our tests failed to discover something that would be a problem for users, and it allows us to make a change in production, which would then, of course, because we have a short development cycle and continuous delivery, make it all the way to the customer very quickly. So that's DevOps. But really what I've discussed to this point is just the first base of DevOps. There's a lot of things you can do that are really sophisticated and I think reveal the degree to which the nature of software development organizations are changing, the relationships between people in those organizations are changing, and their practices are changing, and it's enabled by technology. My favorite example of this is the automated failure detection or failure generation, I should say, at Netflix with Chaos Monkey. Netflix developed a program called Chaos Monkey, and it lives in their cloud. So Netflix runs on Amazon's cloud. They have all sorts of computers that are spun up all the time, and databases, and different kinds of caching layers or whatnot, and they account for a huge amount of the traffic every evening in North America. Well, what they want to know is that their code is error-proof or it's resilient. It is resilient to failure of these resources in the cloud. And so they created a program called Chaos Monkey that literally identifies resources within their network and kills them. So it might identify a computer or a database or a network connection or some kind of security group, and it takes it down entirely. It makes it go away. And what Netflix wants to know is that their website continues to work as expected. And their Chaos Monkey program runs not just in dev, testing, QA, it runs in production. It's an amazing thing, and it's on by default. So if you're working at Netflix and you work on code, Chaos Monkey is running, and it will randomly kill things upon which you depend. And so you have to design your code to be resilient to those situations. And so really, as you can see, it's a story about automation of the development and ops processes that's enabled by virtualization and cloud computing, which is fundamentally changing the way in which organizations produce code and deliver value to their customers. And it's a substantially more efficient process than the traditional breakdown within a software development organization between dev and ops and QA.